yeah, I mean, I was joking earlier on. I said I was feeling like dessert on a buffet table. Just hoping everyone is interested. But I understand if you guys are already too full with everything that's been going on during the day. So this talk is gonna focus on really introductory materials to GPU programming, and this session is structured to engineers at all levels. I'm gonna talk about introductory stuff, and then later on I'll go through some profiling work as well. I'll not be able to show some of the stuff that I wanted to show because we can't, for instance, display the profiler on the screen, but that's okay. I've got some slides to back up the conversation. And yeah, so my name is Fred. I've been a software engineer at Intel for the last 10 years or so. I've been working on different platforms, NPUs, GPUs, and very excited to be here today. And thank you guys for coming for the show. So let's just dive into it because of time. So a lot of stuff get thrown around when people are talking about GPU, and this slide is just to bring some more context into some of the acronyms that people throw around when talking about GPU stuff. And you might hear some of these acronyms pop up later on in the presentation. So for instance, DGPU is nothing but just discrete GPU. So the D part stands for discrete. And discrete GPU is a standalone GPU that has its own cooling mechanism, has its own video RAM, and so on. And we also have the integrated GPU. So integrated GPU is fused together with a CPU, does not have its own cooling system, and does not have its dedicated memory. So typically, DGPUs are more performant than iGPUs. And when people talk about TDP, they just talk about the power that the GPU needs to run. So TDP of a GPU is, in other words, the amount of power it dissipates under the heaviest load at peak performance. So this is becoming very interesting in a world that is trying to be green. So a lot of GPU vendors are trying to say, I can give you this performance per wattage, per this watt, and that kind of stuff. So that's why TDP is equally important. And we do have flops, floating point operations per second. This is mostly used to determine the performance of a GPU. So you typically typically hear people talk about this GPU gives you this much teraflops in this kind of computation, and so on. So flops is just for the performance, and then overclocking is just overclocking. So overclocking is I don't want to say tampering, but overclocking is changing the default clock speed of the GPU just to push more juice out of the GPU. Sometimes it works, sometimes it brings you more problems. And this slide simply shows how GPUs and CPUs differ inherently. And CPUs are considered to be smarter than GPUs in many things. So CPUs can do fancy things like predictive execution. CPUs can do a lot of fancy things. But then on the other side, GPUs can do a lot of work quickly. So the good thing is that you don't have to decide what to use. You simply cherry pick what works best for you. So questions come about when do I use the GPU and when shouldn't I use the GPU? So if the CPU can do the computation quick enough, then you probably don't need to do GPU. You don't need to offload it to the GPU. And if your workload is memory bound, that will require you to transfer a lot of memory that the GPU cannot even hold, then you probably want to keep it the CPU, because the amount of memory transfer happening between GPU and CPU somehow have a big implication on performance. And we've got the Amdahl's law, which simply speculates how much speed up your workloads can have by being offloaded to the GPU. So the formula is 1 over 1 minus P, where P in this case is just a fraction of your workload that can be parallelized. So for example, if this P value was half, so let's say you can parallelize half of your workload, then theoretically the maximum speed up you can get is 2x. So sometimes this can be a good indication to make you make an informed decision. Do you want to offload your workload to the GPU or don't you want to? So if the amount of work involved is too much and the theoretical speed up is minimal, then you probably don't want to go through that. So it's the responsibility of the engineer to decide, does it make sense to offload it to the GPU, or does it not make sense to offload it to the GPU? So interesting interesting observation to make from the slides. So GPUs are special in the way that, in the sense that they use direct memory access, so they can directly communicate to the memory without CPU. And later on in the slides, we'll be seeing how this is used to transfer data from the host to the device. And yeah, so that's it. So why is this important and why should you bother? So if you think about your traditional for loop, where you iterate through a number of elements, in this case, let's think about millions of elements. You can look at the right side. We've got the traditional for loop, where you iterate through an element at a time. And we've got a kernel, which is associated with the GPU. So the kernel simply performs the same operation in in single instances of the elements in your input array, for instance. In the CPU, we can try to achieve some level of performance. We can try to say, let's use advanced vectorized instructions, for instance, like AVX512, try to pack the data and operate on it at a go. But then we cannot achieve this level of parallelism. And that's why GPU comes very handy when it comes to big data that you need to perform the same operation on different data elements. And we are talking about millions of elements in this case. So if you are talking about 10 elements, then it doesn't make sense in a GPU scenario. So the amount of data has to be large, and in order to make sense for a GPU kernel to work on it. So that's why it's important to think about the limitations that CPU parallelism poses and how the GPU tries to overcome this by its design. So when you are talking about GPU programming, there are different frameworks out there that you could use. So we've got OpenCL, which is battles tested. It's been there for a long time, and most of the other frameworks sort of try to address issues that arise from using OpenCL to a certain degree. Some issues are not solvable just because different vendors are pushing for different architectures and different agendas in their platforms. And we have SYCL. So SYCL is what we will be focusing on today, just because SYCL is more in line with C++, and it uses lambdas, templates, and so on, and it gives a more natural feel or a more natural harmony between existing C++ code and GPU. So we're going to be focusing mostly on SYCL. And of course, we have CUDA, we've got Metal, we've got Vulkan, all from different vendors doing more or less the same thing, but in different ways. So sometimes you want to target a specific vendor GPU. So let's say you want to target CUDA in your workload. You want to target NVIDIA GPUs in your workload. There are libraries, CUDA libraries, that you could leverage on to get even better performance. Or let's say you wanted to target AMD specific GPUs. These GPU vendors provide extensions to these GPU programming frameworks that can be used to get vendor specific optimizations in place. So it really depends on what you want to achieve. If you're trying to cover all GPUs out there, then you know what to go to. If you're trying to cover specific vendor GPU, then you know what to choose. So the whole thing about GPU is the CPU has got the data, it needs the work performed, transfer this to the GPU, give it a task to do, then the GPU does the task quickly, and then once this task has been completed, the result is copied back to the CPU. So that's the entire GPU-CPU arrangement. And from this diagram, you can see how this works out. So you typically hear me talk of hosts when I'm referring to CPU. So the host will typically submit a task to the GPU, and then the GPU will do the task, and so on. So these are different constructs of SYCL that we will later be looking on in slides that follow. And SYCL is worth mentioning that SYCL is royalty-free, is cross-platform, and it borrows heavily from OpenCL. And good thing about SYCL is that it's a one source framework, in the sense that your device code and your host code are all executing on the same file, and you're actually using constructs that you're already familiar with. These are C++ constructs like lambdas and so on. So that's that. And then the next slide, I want to show how SYCL interfaces with the entire ecosystem. So SYCL has a wide range support, and this is why maybe its popularity is growing, just because you can cover a lot of vendor-specific optimizations, and at the same time, you can have your kernel run on different vendors. So it provides specificity and generalizations at the same time. And for example, in our case, we will be using the DPC++ Intel compiler. This comes with one API. And if you look at the slides, you'd see that you can actually run your kernels on different GPUs. You can run it on NVIDIA GPUs, you can run it on Intel GPUs, AMD GPUs, FPGAs, and so on. So most developers want a scenario where they write the code once and run it everywhere. They don't want to get involved with the fragmentation and vendor specifics. So SYCL, I find SYCL to try to address that in a decent manner, and that's why I thought SYCL would be a good framework to use for this talk today. And we've got SYCL constructs, so I just want to go to SYCL constructs. So I don't know if the guys can see at the back, but maybe if you cannot, feel free to move forward. So this is a typical SYCL piece of code. Doesn't do anything out of this world, but it shows you the simplicity, like how you can immediately start writing your kernel using the language that you understand most. And it starts like a normal C++ code. You've got the main function and you've got the queue. So typically a queue is the data structure that the CPU will submit tasks to. And once these tasks have been submitted, the GPU performs these tasks using a kernel. So a kernel is the actual function, and this is the kernel in this case. It's a device, it runs on the actual accelerator, so it could be a GPU or an FPGA if you like. And think of a kernel as a function that runs across many elements of your input data. So you simply pass the data, and then the kernel does the computation. And then after this is done, this is written back to the host. So this is all in a single file. You can see that the part that is labeled as host code runs on the host, and then the device code runs on the device, and host runs on the host. So maybe one thing worth mentioning as well, you'll notice that if you look at the SYCL kernel, you'll notice that the in-scope variables are passed by value. So there's a good reason for that. So most modern GPUs are based on little engine, so the memory ordering. But since SYCL was designed to address portability, it tries to make it possible to run your kernels across different devices. So in that sense, if we pass the variables by value, it means that first, each item in the kernel is going to have its own fresh, independent copy of the piece of data that it's working on, and we don't need to worry about the GPU or the accelerator having a different memory ordering scheme. So that's why you'd see the values are strictly passed, the variable are strictly passed by value. And that's really just the basic of it. Simple single file that summarizes everything. So you're going to be seeing more of this later on. So if we now try to dig deeper into the constructs, I think the first interesting one is work items and work group, how the GPU looks at a piece of task. So the way GPU is architectured is that there are many execution units capable of doing work that is submitted to it. And in that sense, a GPU sort of uses a divide and conquer approach in actioning or executing tasks. So you typically find that data or work that is the input is broken down into different work groups. For example, in our case, we've got an 8 by 8 64 work items, but these have been grouped. So you'd see different 4 colors. We've got 2 variations of yellow at the top and then green and blue. So those are the different 4. So this is the first work group. This is the second work group, third work group, and fourth one in no specific order. So inside the work group, you've got work items. So 4 by 4. So the idea is that this work group here contains 16 elements, this one 16 elements, and so on. Later on, we're going to see why this is important. But the whole idea is that we are employing a divide and conquer approach, where we're just grouping the stuff together and acting upon it. So in SYCL, we've got different ways of referencing the stuff. So later on in some of the code that I'll be showing, you'll see how this comes into play. But ideally, if we just look at the global ID, simply is the ID of this specific work item in the entire input. So for example, this specific work item will have an ID 0, 1, 2, 3, 4, 5, 6, 7, 8. But then this work group will have its own identity as well. And this work group will also have its identity as well. So it essentially means that a work item in that work group will have a local ID, but it can still be accessed globally. So the whole idea is that you're just trying to divide elements and also making it possible for the elements to be accessed in their work groups and in their local groups. And yeah, I'm just gonna quickly go to the next one. So there are different SYCL memory abstractions. How do you move data from the host to the GPU or to the device in this case? And there are 2 options. It's really your preference, what you're looking for. So we've got the abstractions, the buffers, which is the first one, and then we also got the unified shared memory. I'm going to be going through the 2 options, and each one of them has got its own pros and cons. So buffers are attractive in the sense that they are self-cleaning and easy to work with. So they abstract the data, and you access the data in a transparent manner without caring, is it on the host or is it on the device? So for example, if we have our key over there and we've declared a buffer of size 10, we have it here, and then we submit the task to the GPU. So buffers need accessors so that you can interact with them. And this is maybe one of those things I don't like about buffers, because it doesn't make sense for you to have another special data structure to access another data structure. But I think they do that for conformity. And in this case, you see that you will always need an accessor to interact with a buffer. So that sort of makes the code lengthy, which I kind of not like as well. Because, for example, if you have 5 buffers, it means you must have other 5 accessors. And this grows, which can be avoided. So anyway, it has its strengths as well. It's easy to use. It's it does a lot of the stuff for the engineer who's writing the code. But one of its other disadvantages is that it's less performant, just because you don't have a lot of flexibility in terms of the things that you can do with buffers. Whereas if we were looking at unified shared memory, so shared memory gives you more flexibility in the sense that you can do more with how the data is transferred. So if you look at this code, it has explicit data movement, you actually need the copy commands to, you need the copy commands to copy data from the host to the GPU. And it is also a pointer-based approach, which is consistent with how C++ or C handles data. So one thing to take note about in unified shared memory, whereas most devices support these, some don't. So before you use these, is always worth checking if this is supported by your device. And SYCL has an API that allows you to actually check if there's support for unified shared memory. So unified shared memory, I'd describe it as a mechanism that makes it possible for both the device and the host to access the same pointer and get the same value. So if the GPU dereferences that pointer, it will get the same value, similar to what if the CPU does it. So some devices don't support it, but most recent devices support unified shared memory. And this is the data abstraction option that is recommended, especially if you are really looking at performance critical kernels. And in most cases, when you are thinking of GPU, you want really to maximize your performance. So my personal, you don't have to agree with me, but my personal choice is unified shared memory. Yes, please.
Layout. Can I configure that the host and device share the same memory layout if considering
alignment? You mean in terms of if you're using unified shared memory?
Probably in both cases. Or I'm assuming that int could be a structure as well.
Yes. So the way alignment works, if you decide to use unified shared memory, so SYCL runtime does the underlying stuff for you, does the alignment handling, for instance. It also does the ordering as well. So the runtime handles that for you. The whole idea about the unified shared memory is that you should be able to declare a pointer irrespective of where it is, device or host, and use it the way you would. So you find that if you look at this first line here, we are declaring it on the host. This part of the code runs on the host. And you see the same item data being referenced here. So SYCL runtime makes sure everything else is working well. So it's the whole point was to make it feel natural for C developers and C++ developers to make it possible for them to manage data chunks between CPU and GPU the way they would in a traditional C++ piece of code. So the SYCL runtime handles that. Yeah. So let's talk about synchronization now. So if you recall the previous slide where we had input data divided into work groups and items, this poses a very interesting challenge because a work item inside this work group can access the local memory for this work group, and it could also access the global memory. However, it cannot access the local memory for this work group. So this requires some sort of sanitization in terms of memory accesses, in terms of synchronizing how these items are executed. So there are three different ways SYCL provides synchronization. So first is host to device synchronization. So normally the host or the CPU will submit some task to the GPU using the queue structure, and this is important because the queue structure uses a dependency graph to check the the correlation between tasks submitted so that the order is preserved, what needs to be acted upon first. And that sort of ensures that there is a good synchronization between device and host. And sometimes it could be that you submitted a piece of work to the GPU, but the GPU is not also available at that time. Maybe another application running on the same device is with the GPU. So this is handled by host and device synchronization. And then we also got the wait still related to this. So wait essentially ensures that everything is completed in the queue. Everything has been, all the tasks that were submitted to be actioned have been actioned, and now control can proceed to the next step. And we also have got memory synchronization. So based on this diagram, a lot could go wrong if we don't guarantee a correct ordering of memory accesses. So the memory fences simply are, you can think of them as primitives that protect memory areas to ensure that there's correct sort of guarantees that there's some sort of correct order of accessing these memory locations. You don't want to access the memory location when the data in that location is still invalid. So you want to access it at the right time. And that's what the memory fence does. And then another form of synchronization that exists is at work group and work item level. So we've got the barrier. So barrier simply is a primitive that forces all the elements to execute it before moving on to the next step. So for example, since a kernel is launched across different elements in the input work, some may execute before others, but it's in your interest to make sure that before anything else happens, you need to make sure that all these work items in a specific group have completed execution to guarantee the correctness of your operation. Otherwise, it's very likely that if this is not guaranteed, that the output that you're going to get is not what you were expecting. So these are the different level or different types of synchronizations that exist in SYCL. And I'm just going to go now to some real world usages. I'm gonna just get a glass of water. So a lot of this, a lot of this talk, I just thought it's important to point out typical scenarios where this becomes important. And to start it off, I had this running on my VS Code, but you just rely on the slides. Hopefully you guys can see the code. So the first example I had is CPU matrix addition. So normal matrix addition. So you have n by n size of matrix. You want to add it to another matrix. And nothing special really about this piece of code. I'm just checking how much time it takes to do the calculation where you add the CPU and where you add the two matrices, A and B, and then you store the results in matrix C, and then you just log the amount of time it takes. And on the other side, I've got the same being done on the GPU. So you can already see from this slide, this is a single function. If you compare this to the previous one, this one is fewer lines of code, and they're doing the same work. So obviously that suggests that when you want to offload your stuff to the GPU, you'll always end up writing more code. And that's why the question of, do I really want to write these extra lines of code? If you don't have to, then you don't need to. So it's always good to check, am I better off doing it in the CPU or the GPU? Because when you do the GPU, it will be more work. So in this case, we're simply taking in the same input, matrix A, matrix B, and matrix C. So matrix C is the matrix that we will store the results of our addition. And in this case, I decided to use the buffer. So you can see we have a buffer for each of the input matrices. And then later on, we also have an accessor for each of the input matrices, for each buffer, that is. So this accessor A is associated with the buffer A, B, and so on. So accessors allow you to define how, or rather they define how you interact with buffers. You may want to interact with buffers in a read-only fashion. So in that sense, you pass the mode as read. You may also want to do it in a write fashion. For instance, this is what we'll be doing in the matrix C, where we'll be storing the results of our kernel addition. And so this is the kernel itself. It's simply taking in these matrix, this index, and adding these two and storing there. Nothing really fancy. And then obviously taking the amount of time it takes to do this. So since I don't have it on running on VS Code, I was intended to show it, but maybe I'll just ask in the room if you guys can guess. So which one is faster between the two of them? So, okay, I'll give more context. I was using 2048 by 2048 matrix. Had someone say CPU? Yeah, you say CPU? That's correct. Why? Do you know why?
There's not enough data to make it work running on the GPU. It doesn't saturate.
Yeah, that's a good argument. Anyone thinks the GPU is faster? Yes?
So I don't think the GPU is faster, but I don't even think it's just about between how big the arrays are, but it's also that you just do one addition more happy know that. Yeah. I don't think it really matters how big you're going to call it. So it's going to last one. No, well, yeah.
So at least we...
Be sure, but yeah, I would say that also affects that. And that you do very few work.
Yeah, it looks like we have a common agreement. It looks like CPU, and you guys are right. I think the CPU was taking 0. Actually, it was saying 0 seconds. And for GPU, it was taking 3 seconds. So this is a classic example of when not to use a GPU. So let's quickly go to the next one, and this is going to be matrix multiplication, and things will change slightly. So, if you think of the traditional matrix multiplication, where we've got two matrices, you have to multiply them and store the resultant in another matrix of this dimension, determined by the dimension of the first matrix and the second one. So you would notice that most GPU functions have got the input variables and matrix A, for instance, in this case, B and C. So C will always be where we store the results. So when you do the CPU matrix multiplication, it does the job, and we log the time. When you come to the GPU one, so this is how the GPU one looks like. I'll just go straight to the kernel, because this side is already, you guys are very familiar with this. So as you can see, we taking, when you think of how matrix multiplication works, you're taking elements in this row, you multiplying and adding in the column of the second matrix. So this is what this kernel is simply doing, right? And right now, we will call this matrix multiplication naive for now, just because it's just faster than the GPU, slightly faster than the CPU, but there's a lot of things that we could do later on. So that brings us to the profiling bit, and the profiling bit sort of makes us understand why this is referred to as a naive matrix multiplication. So I use, there are different tools that you could use to do profiling. You can use AMD GPU Profiler, you can use NVIDIA Insight, you can use Intel VTune. There's so many of these tools out there that you can use. And for this specific presentation, I used Intel VTune. And even though I'm not able to show it, I did have some screenshots that I wanted to share. So when I profiled the naive matrix function that we just saw in the previous slides, and these are some of the insights that VTune showed to me. So the general optimization strategy when it comes to GPU kernels is you want to increase GPU occupancy, and you want to reduce the amount of time the GPU spends installing. And you also want to reduce memory accesses as much as possible. So if you look at this area of the slide, VTune kind of tells you 59.5% of the time spent on this workload on the GPU, even though the GPU was active, it was just simply busy waiting. And it also goes ahead and highlights this as well. It says a significant portion of GPU time is lost due to stalls. So, use that to find that. So the way the VTune profiler works, I was going to show it, but I'll describe it. It's very simple to use. You simply go and select your executable file and you just run it. And that's it. Once it's done running, it gives you all these insights. So based on this, we know that a significant portion of GPU time is lost due to stalls. So it means that for the most part, the GPU is just waiting for data to be transferred from the host to the GPU memory. And that's what I wanted to change in the previous code that we had. This previous code. So if you look at the kernel, we see if we want to reduce the memory, because VTune tells us that we are spending too much time accessing the data from memory. If you look at this loop, we see that every time we multiply the elements from the A and the B matrix and add them, we are reading from the C and writing back to the C. So we are really accessing the C matrix unnecessarily, and this is in the global memory. So this is also expensive. You could argue that it's in the L3 or L1 cache, but in this case, we are really just accessing it from the global memory. As you can see, this buffer that was passed in, and this we can do better than this, and that will be the first step in optimizing this naive matrix multiplication. So what I did in the previous, in the next slide, the code, I have the code here. Same kernel, I just did two things. I reduced the global access by using a placeholder local variable. So I came here, had this variable, tres, and what I'm doing, every time you declare a variable in a kernel, that variable is stored in the private memory. Private memory is fast to access and easy and performant. So I keep on doing this in the loop, so I'm not doing it on the C anymore. And then once I'm done with this loop, I simply write it to C. So I'm only accessing this once. And the other thing I did, if you look at our previous kernel, we had a lot of these computations, j plus n plus I. It is trivial computation, but if you're doing it over a million elements, it starts to add up. So we can pre-compute this as well, and use placeholder variables and have a more optimized kernel. So if I can just tell you guys theoretically, the previous kernel that we had, the naive one, took 16 seconds, and this optimized one took 6 seconds. Just by the fact that we reduced the memory accesses, that was enough to give it over 50% performance boost. So the general optimization tips to optimize your GPU: you want to maximize GPU occupancy, you want to minimize global access and divergence as well, and so on. So I think some of this stuff we've already spoken about. Just want to leave time for. I've got this online. If you want to try it at home, you want to download it and run and test the things, you're welcome to do so. This is homework. The previous matrix multiplication that we did, if you want to try it at home, we still have lots of rooms for improvement. If you think about how a matrix multiplication really works, is you are accessing these elements and these elements, storing them there. So think about how we can exploit call list memory locations to improve this even further. And this would improve our matrix multiplication even further. So matrix multiplication is come up frequently because if you think about neural networks, if you think about the convolutions, it's a very common operation. And that's why it's a very good case for offloading to GPUs. So yeah, and above all, don't overdo it. Just keep it simple and don't overclock your GPUs. So if you want to download the slides and you want to try it at home, you can scan the QR code and get it. So I think I still have 5 or so minutes. So 10 for any questions in the room. Yes, please.
For the talk.
Okay.
Can't an optimizer take care of this so that we can just, for the CPU, the optimizer does these kinds of optimizations?
You mean the parallelism? Yes. What does it do exactly underneath? Because I know, for instance, you could use some advanced instruction sets on the CPU to get these kind of optimizations, or you could also do loop unrolling and so on, but it will never get to the level of a GPU in terms of the number of items that can be executed simultaneously. For example, if I think of the biggest advanced instruction set, I think it's AVX512. You can put in, I think, 64 data points and act on them. But even in a tiny GPU like the one I was using for this content, the local size group is 256.
I actually mean from the compiler point of view.
Yeah.
The compiler could do the optimizations for me. I actually don't want to do anything, just write the same code and not optimize, leave the compiler.
All the ML
On the GPU.
Say that again?
GPU execution.
Because I think vectorization, and we just got the explanation that it won't, even vectorization is not going to help you with you. The radio is a little larger.
Even instead of writing a kernel, you write C++, so then magic turns it into
This example, the vector would have been too large anyway. AVX wouldn't have helped you. So that's what, for example, the optimizer would do, depending on your optimization.
So if you're doing it on compiler, you mean like you could achieve the same level of performance on CPU? It's yeah. Yeah.
Complicated because you need to think about how to organize these things in memory. Instead, like I just write C++ code and some magic AI turns it into cap.
I mean, the good thing is fair enough of a question. The good thing is the way SYCL is meant is to make it easier for you. If you look at the equivalent OpenCL, for instance, kernel, it's quite complex. And what I've seen is that there are libraries that you can already use that has the kernel in place. You just pass the input and the output matrices, and it does the job for you. So one good example from Intel is the 1MKL library. And I'm sure NVIDIA, I'm sure AMD has all this. So they use hardware accelerators to even make it even better. It's complicated to write, but then the good thing, this is all abstracted. So yes, there are ways you can make it simpler by using existing libraries or functionalities that can do the kernel stuff on your behalf. But then this talk is meant to give you the opportunity to understand what's going under the hood. Because I find it useful to just have an idea so that if you don't get the performance you want, you know where to start looking at. I think someone had their hand raised up. Yeah.
Enough of a related question to the optimization. So
yeah. Yeah.
Optimizing compiler, right? So
yeah.
At least that's why the compiler knows that the point is not ABS.
Yes, that's
should be able to do it
itself.
It depends on how you write your kernel. I've not seen where you pass magic parameter and then SYCL does the thing for you. Most of the stuff SYCL tries to do is to prevent you, the developer, from writing a lot of code to do your kernel. So this is already, if you look at equivalent in OpenCL or Vulkan or something else, this is already minimized. But if you are to do this on the CPU, remember all this is running on the GPU, and GPU does not have ways to do smart things. It just knows this is the data element, this is the operation, let's get it done. But if you are to do this on the CPU, then the CPU, I think the compiler can be smart enough to optimize this actually. But then when you come to the GPU, it's upon you. And this slide, I wanted to demonstrate a simple optimization, like just reducing memory accesses can actually improve the performance of your kernel by 60%. Another optimization that you could also do, which is part of the homework, is you can use local memory as well to even improve it further. I got this matrix multiplication down to 0.01 seconds from 16 seconds, where it had the naive, 16 seconds was CPU, I believe, and then the naive matrix multiplication was around 6. So this, after optimizing further, it gets to 0.01. And it just shows you the possibilities, the things you could achieve by doing simple optimization. In most cases, when you're writing GPU kernels in real world, you have responsibility of the entire pipeline. You have access to the code where you submit the actual work to the GPU and write it back to the CPU. So it becomes sort of your responsibility to make it worthwhile, choose the GPU and get the most out of it. I don't think you can pass any flags and SYCL to it. What you could do is use existing libraries that have been highly optimized, like CuPy. Someone talked about CuPy earlier on. They have underlying implementations that you can already use. But the only problem is that those are vendor specific, which people also don't like. People want to be able to run their kernels in different devices, prevalent in the market, and those coming in the future. Think someone else? Yes?
Actually have time for any more questions. We have a closing keynote happening.
Okay. Sorry, we can talk about it.
Yeah.